Anyway, we measured the cosmic heat radiation in a couple of different ways, and I'll show you the results. And we also looked for the light from the first galaxies. So this is the chart that got me a standing ovation at the Astronomy Society. It shows a smooth curve, which is the prediction of the Big Bang radiation, and the little boxes that are the measurements, they fall right on the curve. This is a prediction for how bright the radiation is at each different frequency, and we were measuring the frequency in waves per centimeter. So these waves are a few millimeters long, typically. So anyway, this ended basically all controversy over whether the Big Bang theory is correct, because there's no other theory that matches this result. And a few people objected, but they died. The second big result is this one. When Stephen Hawking saw this chart, he said it was the most important scientific discovery of the century, if not of all time. And the chart he was talking about is the little oval in the lower right-hand corner. I should have made you a bigger one. But that chart shows a map of the Big Bang as seen from here. So this heat radiation that comes to us almost equally from all directions isn't exactly the same in all directions. And so there's hot and cold spots. And these hot and cold spots are thought to be the result of whatever made the Big Bang. So there's the hot spots turn out to be the ones that are less dense than the average, and the cold spots are the ones that are more dense, and the cold spots are the ones that are going to grow up to be clouds of galaxies and places where people could live, and the warm spots are going to grow up to be empty. So that's why Stephen Hawking was excited about this. This tells us now how to start understanding the formation of everything after the Big Bang. So and we also now know that if those spots weren't there, we could not exist, according to the understanding of science that we have. If the Big Bang had been totally uniform, galaxies and stars never would have existed. So we're here because of that, in a way. So culturally, this is more important than I ever knew. So the more scientific papers have been written about that little oval than there are pixels on that map. Thousands and thousands of science papers have been written about that. So this is what they said 5 years ago when I got a phone call on a Tuesday morning from Stockholm at 5:30 in the morning, or 5:45. They're giving us the prize for discovering the black body form, which is the curve with the little boxes on it, and the anisotropy. In Greek, that's Greek. It means not the same in every direction. It means this universe has pimples of the cosmic microwave background radiation. So we'll get to what the new discovery is in a bit. So this is me showing my chart and me getting my diploma from the King of Sweden. So our friends are going to go do this on December 10th. And this leads up to the surprise. In 1998, this picture came out in the New Yorker magazine. The caption, if you can't read it, says, "Everything we know about the universe is wrong." So the guy is watching TV, and that's what the announcer says. So now I'll show you one of those things. In 1998 or so, it was discovered that the universe is accelerating. Einstein had put a place in his equations where this would be allowed, but astronomers, for the most part, said, "We didn't ask for that, we don't want that, it must not be." We were a little prejudiced, I think. At any rate, those three fellows on the right are shown as they were receiving the Shaw Prize in Hong Kong 5 years ago for this discovery. So what they found was that distant stars, distant supernovae, which are like standard candles also, were about 20% fainter than they should have been if the old theory was right. So 20% fainter, they're about 10% farther away. Well, that's actually pretty important. So it means that when you divide the distance by the speed, you get the wrong answer by about 10%. So that means the universe has been accelerating over this period of time. And so not decelerating, but accelerating. So totally not understood. All we know is so far that Einstein told us it could be, and we all ignored him. Not everybody. A few people were expecting it, but most people were not. So this is a graphic. This shows that we all thought that the galaxies are going to attract each other, and therefore the expansion will slow down, but it wasn't so. It also means that there's a changing mix of material in the universe. As the universe expands, some things change. The universe expands, the contents get diluted. Material particles like us, they get spread out The heat radiation from the Big Bang gets fainter and fainter. Earlier on there were neutrinos that mattered a lot. They don't matter much now. And earlier on, when the universe was much smaller, this dark energy, we call it, that causes the acceleration, it didn't matter. If you were an astronomer 1 billion years after the explosion, you would never know about this dark energy stuff in the accelerating universe. Our young friends here never could have found it because it hadn't happened yet. So there's a little bit left to figure out. So I'll show you coming up the idea about the new telescope that we're working at Goddard Space Flight Center and around the world to do the next big thing in astronomy. So there's plenty of things we don't know. And this little chart summarizes some of them. Where did all the antimatter go? Physicists think antimatter and matter are the same, except opposite. So how come they're not equal amounts of both? We don't really know. What about the dark matter? As it turns out, there's a substance called dark matter. Astronomers are very sure it exists. It's much more abundant than ordinary matter. And we determine that it exists because it has gravity. And that's all it has that we know of so far. But we also wouldn't exist if that stuff didn't exist, because that was responsible for all the hot and cold spots in the Big Bang. So because of dark matter, we're here. We can only barely detect that it exists. Nobody's ever seen a single particle of it in the lab yet. So a lot of things that we don't know, but a lot relating to our own history. And I think that's one of the things that fascinates people about what astronomy does. We can work out our own history with this story that begins with astonishing early universe, which we can barely imagine or describe, and then comes to the specifics of the history of our own galaxy and our own solar system and our own future. So this little chart just talks about infrared light and the fact that it's different from visible light. Infrared light has longer wavelengths than visible light, and you can't see it. Maybe you can feel it. If you're near a candle, you can certainly feel it with your skin, but you can't see it. So it shows us different things. So the picture of the space shuttle, the picture of an astronomer, the picture of a cat, they're all different when you use infrared to see them. And so similarly, we learn different things about the early universe with infrared light. And it's tricky for us because infrared that we want to study doesn't come through the Earth's atmosphere. We must go into outer space to be able to use a big telescope. And that's what makes our new observatory so difficult and challenging and exciting. So this is what it looks like. It's a telescope that doesn't look like a telescope. It looks like a solar energy concentrator out there. And what really is a galaxy energy concentrator. Light comes from the far right, bounces off that big gold hexagon, is focused onto a small mirror that you don't see, and bounces into the instrument package where we turned it into spectra, which are rainbows and pictures. And so all the data will come back from outer space by a radio link, just as it does with the Hubble, only it's farther away. This is an international partnership project. The European and Canadian space agencies are chipping in large parts of their budgets to make sure this happens, and they're sending us instruments. The Europeans even buying the launch vehicle. So when we want to go to space, we take our telescope down to French Guiana and put it on a French rocket, or European rocket, the Ariane. So let's see. So when are we going? About 2018. It's supposed to be sooner, but it isn't. So this is a full-scale model that we had, that we're taking it around various places in the world. The company that's our prime contractor likes to show it off because they have other government agencies they want to sell big telescopes to. And this is what it looked like in Washington and Munich. And in a few weeks, it's supposed to come to Baltimore, to Science Center. And they put it out in the parking lot, I think, just outside the Science Center. And we expect Senator Mikulski to come for that. So we're very proud of that. Oh, golly. Time for you to do something. I'll be back. Okay. So how it works. Well, number one, it's a big telescope. It's in outer space. We need to protect it from the sun. So we have a giant umbrella. The umbrella is comparable in size to this room. It's as big as a singles tennis court. So, and it's made out of 5 layers of thin plastic coated with metallic coating so they reflect the sun. And so hiding behind the umbrella of the telescope will come down to very low temperature, about 40 to 50 degrees Kelvin, which is plenty cold enough. And we need it to do that, otherwise it emits infrared all by itself and we can't see the sky. So that's number one tricky thing. Number two, it's got to be 1 million miles from Earth so that it can get cold. So this is something we have been doing with other observatories, but it'll be new for this one. It means that astronauts are not going to go there and fix it because we don't have that technology now. Maybe we will, but we don't now. And the third thing it means is the telescope's bigger than a rocket. So you see in the upper right picture there's a picture of the telescope all folded up like a butterfly in its chrysalis. Every cubic inch is used. So after we get it up there, then we push the buttons figuratively, and it unfolds. And I think I have a movie showing that. I hope so. Yeah, let's see if it works. This is a movie of the unfolding of the observatory. First, we pop out the solar panels. Then we pop out the telemetry antenna, a little parabolic antenna that sends the information back to Earth. Now we unfold the sun shields. And by the way, this happens about 10,000 times faster in the picture than it does in real life. We'll be slow and cautious. If you're a mechanical engineer, you realize this is an extremely challenging problem because there are hundreds of mechanisms and everyone has to work. So we have to rehearse this out of town before we take it to the big time. We have lots and lots of rehearsals planned for this. Eventually, the sun shield unfolds and the telescope will come out. Our prime contractor, by the way, is Northrop Grumman, and they say this is definitely not the most complicated thing they ever put up in outer space. But they can't tell you much more. But it's probably a good point to say that we astronomers could not be asking for this kind of project if somebody else didn't also care about big telescopes in space. So there it is. It's almost finished. Finally, you get the great hexagon of 18 smaller hexagons all put together to make the great telescope. Oh, we've got a picture to show you where we're putting it. It's a place called the Sun-Earth Lagrange point. This was actually discovered in 1750 by Euler, great mathematician, and these are places where you can put an object and it will sort of stay in the same relative position with the Earth as we all go around the sun once a year. So it's a good place for us. This observatory stays more or less in the same place the whole time and doesn't get away. This compares the size of our telescope with the size of our precursor telescopes. The Hubble and Spitzer telescopes there's little circles in the upper row, and there's our giant hexagon. And you can say, well, why do astronomers always want bigger telescopes? Well, two things. One is the light we're trying to find is pretty faint, so the more you can catch of it, the better. And number two, light is a wave, which means it makes a fuzzy image. No matter what you do. So the only thing you can do is to make a bigger telescope to get a sharper image. This is called a diffraction problem. So bigger is better for us, and colder is better for us because of the infrared. So now you know why we have to undertake such an amazingly difficult engineering program to do this. Just a tabulation of the 4 different instruments. I won't dwell on it, but we have cameras and spectrographs that cover the entire wavelength range from 0.6 microns, which is more or less the red laser wavelength that we would have if I was using the laser pointer, to about 28 microns, which is heat radiation that your body emits. By the way, each of us is emitting about 500 watts of heat radiation right now today. And similarly, if you point this telescope at a bumblebee at the distance of the moon, you can pick up the heat that it makes. So we're doing pretty well with the building the observatory, technically, at any rate. We had to grind and polish and coat 18 big hexagons of beryllium. Each one's about this big, and you could lift it if we would let you. Which is a truly amazing mechanical engineering accomplishment. It's beryllium. It's a couple of millimeters thick. And it's very carefully cared for and machined and polished by techniques that are company secrets. So even I have no idea how they really do it.